Good afternoon. Welcome to this talk about research-based visualization techniques for presentations. Very happy to see a full house here. That's really exciting for a research talk. Those don't tend to, well, it's a small room, I guess, but still, it's nice. My name is Robert Cosera. I'm a research scientist at Tableau Software. I'm also some of you might know me as Eager Eyes around the internet. I'm also a former academic. I keep doing this wrong. With academic audiences, I usually say I'm a recovering academic. So I used to be a professor at UNC Charlotte for 7 years, and then I started a sabbatical at Tableau in 2012, and then decided to stay there rather than go back to academia. And I usually like to start my talks by showing some silly pictures. So I show things like this one. This is, I like to run. This also shows me as a natural leader. And oops, sorry about that. And in this case, I wanted to establish my research credibility with the worst selfie you have ever seen. And I will never show this again. But this is the first selfie I ever took. This is true. This is about 10 years old. So this is me in my office in Charlotte wearing my regalia. But we shall never speak of this again. With these talks, we usually, I hate these overview slides. Like, here's what I'm going to tell you, and then I'm going to tell you, and then I'm going to tell you what I told you. But we were told to have an overview slide, so I figured, OK, I'll make you an overview slide. So this talk will be about presentation. I will start by talking a bit about what that means, and then I'll talk about 3 different techniques. One is the connected scatter plot, one is called isotype, and then I'll talk about pie charts, which may come as a surprise, because pie charts are this weird thing that we don't talk about in visualization. But they're actually not that bad, and I will talk a little bit about some research we've done. So all of this is based on research, hence a research talk. So the main overarching idea here is that we need to think about presentation as something that's different from analysis. And when I talk about this in the abstract, I suppose many of you would probably agree with me on that. But there's something much deeper about that you have to really internalize to understand what that means, or what it should mean to think in terms of presentation. And that means not just here I'm presenting rather than analyzing data, but what are the tools that I use, what are the techniques that I use, and how are they different. And I'm going to show you a few things that are quite different for presentation, and I'm going to argue that they are much better for presentation, even though they can actually be horrible for analysis. Pie charts. But that's kind of the idea here, right? So let me give you an example. I hear there's an election going on here. So this is election-related data from the early 80s, or I guess throughout the 70s. This is about House and Senate campaign expenditures in millions of dollars. And you can see these numbers, and it's a bar chart that shows you these numbers over time. And you could say, well, OK, those have been increasing, I guess. Well, it's just a bar chart. It's kind of boring. I could make it more exciting by giving it a cool title. I could say, these are monstrous costs, right? But that's still not all that exciting. How about this? Has anybody seen this before? OK, wow, only 2 people. Interesting, 3 people. Wow. Good, well, that's good, because I get to introduce a few new people to this. So this is a graphic that was drawn by Nigel Holmes I think in 1980 or 81, for Time magazine, and it has become a bit of a crystallization point for a lot of research recently in information visualization that looks into how we should represent data for things like memorability and other topics. To briefly walk you through this, why is this a bad chart? Right? So this has been torn apart by lots of people, and obviously, there are problems here. So there is the teeth here that are the bars of this bar chart are triangular. We've done some research on that. We know that you underestimate those values. The whole chart is distorted. The baseline isn't level. It's not straight. Everything's in this weird kind of projection, and it's hand-drawn, so it's not any kind of easy projection. And then there's this whole freaking monster there that obviously doesn't have to be there for a bar chart. But then there are clever little things that make this work for its purpose. One is it draws your attention. This was printed in Time magazine, so this was back in the days before the internet. or before anybody was actually on the internet, I guess. And so it was a small part of a page, and it was supposed to draw your attention, and that's certainly what it did. There are a few little ideas here that are quite interesting. I'm going to try and point with my mouse pointer here. Or maybe I won't. Where is it? There you go. So when you look at this, there's a little vote button there. That's kind of an interesting thing. And the tail of the monster looks like a dollar sign. And the thing I actually wanted to point to, if I can do it, is these spit bubbles there. They have reflections that look like dollar signs as well. So it's a bunch of little things that are just interesting devices that you will remember after this talk. If nothing else, if I wake you up next week at 3 in the morning and shine light in your face and I'm like, what do you remember from this talk? First thing you're going to say is, get out of my house. And then the second thing is monster, either because you say you monster or because the monster. But you're going to remember this. This is a thing that's going to stick in your head because it's unusual and it has lots of little hooks into your memory. It has connections with the other things that you know about elections. So that makes this an interesting chart, but it's not the kind of thing that Tableau does. It's not the kind of thing that most people will tell you to do. I'm going to move this, I'm sorry. I'm going to try not to hit it again or blow on it. So this is not the kind of chart that you would get from Tableau or the kind of stuff you would see in a lot of the best practices talks. But it is effective for other reasons. So I'm going to argue that there are these two extremes here, the boring, plain bar chart and the monster on the other hand. But they're really a sort of continuum, and we can find a middle ground where we can do things that are more interesting than the bar chart, but not quite as extreme, but also not quite as bespoke as the monster, because that monster was drawn once by hand for that particular purpose, and you're not going to reuse it for other kinds of things. So thinking about this in slightly more researchy terms, there is a certain way we look at visualization techniques where we think about what do we want a technique to do. And this is going to be a very incomplete list, but I just picked like the top 3 things that you would usually want from a technique. One is it has to fit the data. That's the entire idea behind Tableau. We know that you have a time series and you have a measure, so we're going to give you a line chart, and then if you break it down by a dimension, we'll break down the lines and so on. So we know what representation fits the data, and that's what the tool tells you or shows you. The other thing is it should be effective. That's more about the perceptual side of it. Can I see the things I care about? Can I compare values? Can I understand the differences in terms of how much more is this or things like that? Can I see trends? Can I see outliers? That kind of stuff. And then both from the computer science perspective or kind of the software engineering side and the research side, we usually like to think of these things as algorithms. So we want them to be general. They should work for all the data and not just work for one thing and not for the other. That would be a bad thing for a general technique and for analysis because we never know what your data looks like. So we want things that probably are going to work. And bar charts pretty much always work. That's why they're popular, but they're also then, of course, always the same. And I argue that we need to give up one of these, the generality, even though I can't say it, and look at techniques that are much more specific and actually don't work in most cases. But as a trade-off, we get a few other things. We get things that are more engaging because they're more interesting. We get things that are more memorable because they're more unusual. And that way people can actually first of all, see and actually want to look at the things that you're presenting and hopefully remember what you told them. What I'm going to do in this talk a few times is I will point you to published papers. These are all stuff that I've written, but because I want you to see that there is stuff here that we've done as actual research and it's published. So here's one paper that I wrote for the Visualization Viewpoints section of the Computer Graphics and Applications Journal or magazine earlier this year on presentation-oriented visualization techniques, where I'm arguing that point in much more detail. So if you care to read more of that, this is what you can. And you can just Google these titles and find them. I didn't even put the whole references on there because I doubt anybody's going to write them down. But if you Google those titles, you're going to find them. They're on my website. So I've shown you the monster and the bar chart. What else is there? And I've argued that there's a middle ground. So what does that look like? So one of those techniques is the connected scatter plot. And this is a technique that's been used in news graphics for a little bit, but that isn't really generally used all that much in visualization. So I'm going to show you what this looks like and then discuss a little bit what it's good for. The way this works, as you can probably figure out from the name, is that a connected scatter plot is a scatter plot where we connect the dots. And what we do is we connect them in some sequence that is usually temporal. So this particular one shows you the number of car fatalities in the US on the vertical axis, the number of miles driven on the horizontal axis, and the line here is time. So it starts in 1950 on the left, excuse me, and it kind of goes up and down, and then it starts going up. And if I reveal more of this, you can see that suddenly it changes direction. And suddenly it goes more horizontal, and then it drops. And then if you go along this further, you see something that you haven't seen before in the line chart, which is a loop. And you might wonder, well, how is this possible? And then you remember it's a scatter plot, it's not a line chart. So time actually goes along the line. And again, the vertical axis is car fatalities, horizontal is number of miles driven. So if those two change at the same time or with some delay, you can get a loop. And the whole thing is annotated, as you can see. So this is a piece from 2012, I believe, that talks about how this has changed over time, and it argues that certain events, certain people have influenced the number of people who die on America's roads, and that's what these annotations are for. So I don't expect you to be able to read those. The only thing I want to point out is that there are little kind of spark lines in each of those individual paragraphs that show you which part of the whole graph they correspond to or they talk about. And so this technique works well for this topic, or this particular purpose, I should say, because it's easy to annotate, because it makes a shape, a gestalt. It makes something interesting out of a bunch of points. If you look at this as just a scatter plot, it's just a bunch of points. It's really not very interesting to look at. But the sequence is important here. And especially when you see the loop and things like that, where interesting things are happening that you wouldn't expect. So the loop, I should point out, is the oil crisis. So what happened in the late 70s, I believe, is that first number of miles driven was dropping, and then the number of accidents dropped as well. And so there was a delayed effect, and that caused that loop. And then the whole thing makes for a very nice whole page layout. So this was printed as a whole page in the New York Times in, I think, 2012 or so. And makes for a very engaging, very interesting piece. You might look at this, you might start reading somewhere along the lines, one of those annotations, and then you read something else, and you can jump back and forth. You understand the temporal sequence fairly quickly, and it just makes for a nice news piece. Again, this is presentation. This is not analysis. This is what this is for. So we found this technique out in the wild, so we took it into the lab and figured, we'd see how it responds if we poke it and see if it'll breathe. And we tried it on different data. And it turns out that it doesn't really work that well in many cases. So here's one I tried. I was like, this is kind of ugly. No. And it turns out that you can actually make a hairball without even drawing a network diagram. So that's kind of an achievement. But it's interesting, though, because this technique has been used. I have about 24 examples that I've collected from all kinds of news media where it's worked really well. And an example here is this one. This is about the helium supply, where it talks about the price of helium and how much helium there is out there. This was done by Katie Peak for Popular Science, and there's also a little story behind it. We run a little conference about data journalism that's called Tapestry, and Katie Peak was there in 2014, I think, and saw Hannah Fairfield talk about the piece I just showed you earlier, and then she figured, well, maybe this is going to work for my data. And she just tried it, and it worked, and she got this nice piece out of it. And again, no details here, but if you just look at the shape, it's really interesting. There are loops in it. There are these L shapes where these sudden changes in direction, and those always indicate certain patterns in those two time series that you're essentially comparing there. You can even use this for, So the thing I wanted to say here is that this is there's a certain survivor bias here. Of course, we're only seeing the successful examples. What I just showed you, those bad examples, are the things you would never see because somebody tries that and it doesn't work, so they don't publish it. But that's why I wanted to show you the negative examples too. One more example. This is from Bloomberg in 2014, I believe. This is an interesting chart because it goes back to where the idea originally comes from. There are a number of papers from the 1940s at least, and maybe going back a little bit further than that, that talk about the UV curve, which is a thing in economics, and I don't understand how it works, but basically what it does is the U is the unemployment rate, and the V is the vacancy rate. And what they do is they plot those numbers against each other over time, and there is a theory that says that those points settle into a shape that's a hyperbola, and that there is a certain parameter, basically the distance from the origin. It tells you something about what's called the natural unemployment rate. And the argument behind this piece is that that has been shifting. So what you see here is that there is that gray band that kind of summarizes the overall numbers, and it shows you, even though you have lots of data here, lots of individual points that don't make a very compelling, nice chart, they kind of smooth it out. And you can see how that shape is going to settle into a different plane here, perhaps. And they also liken it to a scorpion's tail, because that's what it looks like. So you can see there's a scorpion there at the top. That's there on purpose, because they're trying to give you a little mnemonic there for that. And we've done some work on this, again, pointing to some of my research. This is with work with Steve Harose and Stephen Falconeri at Northwestern University, where we looked into this. We tried it out with in a number of different ways. We looked at memorability. We looked at how well people can understand this technique. We tried to see what people actually remember about it, like do you remember the L shapes or the loops and things like that. And it turns out it works really well. It's an effective technique in terms of understanding. It takes people some time to understand what's going on. But if you actually ask them, so here's what that shape looks like, what if one value goes up, the other one goes down, which direction is it going to go? And people can actually tell that. So we were quite surprised by that. It works better than we thought. This was just presented at the Viz conference 2 weeks ago and was in the transactions for visualization and computer graphics earlier this year. So this is one technique. The technique works sometimes. It doesn't work in general. So I don't have numbers for this, but I would say that in 90% of the time, if you try it on your own data, or even more than that, 95% of the time, if you try it on your own data, it's not going to work. You'll just try it. It's actually really easy to do in Tableau, but you'll see that it just makes some hairball and it's terrible. But when it works, it's really worth it because it's really unusual and it's really interesting. And it's one of those techniques that can work sometimes and be really interesting for presentation. The second one I want to talk about is another one that we kind of found in the wild and tried to figure out how it works. This is called isotype. Has anybody heard of isotype before? I see a few people nodding, but not a lot of hands or any hands. OK. So isotype is a horrible acronym that it stands for the International System of Typographic Picture Education. This was coined by Otto Neurath in the 1920s, and he developed this with his wife Marie Neurath and Gerrit Arndt, who designed a number of shapes that that may look familiar. These are kind of the original ones that Arndt designed. But many of the signs that you see, I'm not actually seeing any in here, but unlike exit signs or bathroom signs, all of that language, the simplicity of these signs, that goes back to what Arndt did. So he turned these, the usual way things would be depicted at that time, into very reductionist, reduced depictions that only used very, very simple shapes. And what Neurath did was to say, well, we can use these shapes to represent data. And Neurath's idea was actually, this was really interesting if you think about it, in the 1920s, to educate people about the world through numbers. To say, well, how are different countries different? Let's look at how many cars people have, how many radio receivers and stuff like that. Or let's look at the history of the Industrial Revolution. This is a chart that shows data over time, and the way it works is that each individual figure represents a number, in this case 10,000 workers, and they're color-coded whether they work at home Or in factories, so black means at home, red means in the factory, and the boxes with the smokestacks, those are factories. I just point this out because sometimes people get confused what those things are, so that's what that is. And you can see how that number changes over the years, and there's a bit of a problem here because one of those steps isn't the same as the other steps, but essentially it shows you a timeline. And then there are these blue shapes that show you the amount of product produced. And that gives you a sense of the amount of output they were producing and how it was increasing over time. You can read this in two different ways. You can look at these shapes and count them, and then multiply that number by 10,000, and you've got the number of workers. Or you can look at this as bar charts. And because they're all the same width, and you can just compare them and say, OK, from 1820 to 1830, the number went up, and then it went down, and so on. So you can read this pretty easily in different ways. The cool thing about representing things this way is that there is no language. Well, there's some language on here, but it's very little. You can understand that this is about people. There are other charts that show things and animals and ships and all kinds of stuff. So you can tell very easily what they're about because you can just look at the images and you understand them. And that's where the international part of isotype comes from. But of course, this is also something that you could call chart junk. There's stuff on this chart that may not have to be there. Is that a thing that's a problem, or can that be a good thing? Does this impede reading, or does it help? Well, does it even help, perhaps, or at least not impede reading? And can people remember what they've seen? So we did some work on this. So again, this is the same idea. We took it into the lab, see how it worked. And this particular technique works well when you have a small number of values to talk about and when you have shapes that are actually different. So if you have data about cell phones, you're not going to do very well because they all look the same now. But if you have things like furniture, so this is my example here, then it's a lot easier. So we created all these examples and showed them to people. This is a study we ran with about 100 people or so. And we had them read those charts and then ask them questions about those. And we compared how well they did, how fast they were, how much they remembered, to a number of other conditions. So we had a basic bar chart there in the top left of the right-hand image. We had an example that had these little bubbles. So they were stacked objects, but they were all the same. And then we also scaled the objects. This is a thing where Neurath said, well, you should not scale them because when you scale in 2 dimensions. Or you really stretch the object, which is really weird. And the last one is our chart chunk example where we had an image in the background and the bar chart in the front. And it turns out that people do really well when you show them the isotype chart. They remember what you showed them, and they can read them really well. They're actually no worse than the bar chart in terms of reading speed and accuracy, and they're much better than the bar chart in memorability. So that's a thing that we found, that people can actually remember what you showed them, it shouldn't be surprising, but that's what we found there. And they're not doing as well with the other chart types. So especially our chart chunk example in the bottom right there was actually quite distracting. So people were getting confused by that background image more than we thought they were, especially because the colors are different. So we actually designed this to not be terrible, but it turned out to not be very good. And again, there's a paper about this that we had in at CHI last year. This is the Human-Computer Interaction Conference, where we talked about that and looked at memory and so on. So it turns out that these techniques can work, and that we have to be a bit more careful about just assuming that because they're unusual or because they have images in them, that they're a bad idea. We also, my colleague Vidya Settler has done some work on finding shapes or images based on labels in your data. And so we could even combine that and say, well, if we could get all of the stuff into Tableau, we could even make those things for you because we could look for shapes for you and build those charts. We're not doing this right now, and I'm not promising anything, but it's a thing that you could imagine being able to do. Are there any questions so far? The fish is just the, what do you mean, significance?
Yeah, I just see in all the other ones, it's dogs, birds, cats, and then there's the fish.
Oh, interesting, yeah. So why is there a fish in the chart chunk example here? It's because the category here was animals, and we used a different shape in the background than we used in any of the others, because we didn't want to we did not want people to see the same shapes twice. So we had a very large number of these shapes, and then you would go through about 60. Is that true? Well, some number of examples. I forget how many. but you'd go through a good number of them, and we would randomize the order and show you all kinds of different variations. And we wanted to avoid you having seen something before, because we asked people about, like, how many fish have you seen? How many parrots? How many dogs? And so we wanted to avoid a wrong connection there by having by reusing a shape in one of the conditions that was already used in the other condition, if that makes sense. Yeah, so the fish is basically just, it represents animal. That's what that does. Yeah.
Going back to the previous slide, the one thing that struck me about couches versus lamp is the amount of ink taken up by the image, right? So it looks like couches is a bigger value because it's probably got 5 times as much ink as lamps, right?
Yeah. So the question is about how much ink do the different shapes use up, and of course the couch is much bigger, and also the desk is wider than the lamps. We didn't find any kind of effect from that, I believe. I think we looked into that because we were worried about it, but we ran. I think we had a pilot where we actually tested for that, and we didn't find anything. So it's because we're very clearly stacking the objects. I think people were easily able to figure out that that's what they should be looking at, and weren't confused by that.
And is part of that then that this works really well for like discrete integers? We're counting.
Yes. Okay. So that's a very good point.
Half couches, right?
Yeah. Yeah. So what we did not try in some of the examples. To go back here. So some of the examples, and I don't have one here right now, but some of the examples they actually had like half images. Like you had. Each, and so one more thing to say here, of course, so I mentioned that each figure here represents 10,000 people. So if your number is 25,000, you can imagine cutting one person in half and then just having 2.5. But in this case, they're not doing that. They're just saying, well, we'll just do full multiples. We just didn't try the cutoff version because we were worried about all kinds of interactions. If you just cut off some of these shapes, they're not actually meant for that. So we didn't want to do that. But that's a good question. I mean, if you and you have to have a multiple, yes. So the numbers we tested were up to 5, up to 15, and up to 20, I think. And people do much better if you have up to 5 than 15 or 20. Yeah. So that's certainly a diminishing return there when you have a lot more objects. This comes back. So there's a term here that I didn't want to mention, but there's a term called because I don't remember the term actually. There's a term it's called subitizing. You can very quickly count a small number of objects even though you're not consciously doing it, and that goes up to about 5. And there is some debate about what that actual number is, but somewhere in that range, 5 to 7, you can count. If I just flashed a number of objects out there and the number was small, you would all do a very good job of guessing that number correctly, even though you hadn't actually had enough time to actually count them consciously. Yeah.
Can you go back to the previous slide where you had the little people? Did you guys do any testing where so like in 1830, they have a box around 5, which makes it easy to count because it's 5. Did you guys do any tests where you sort of group them together so it makes it even easier to count?
That's a good question. No, we did not. But that's a thing too that we should try out at some point. Yeah, that's interesting.
Yeah, I would think with when you do unit charts, if you can organize them that way, it makes them very easy to count, right?
Yeah.
So.
Yeah, you could just do multiples of 5, and then that way it would be much easier to count them. But yeah, that's an interesting point. We should try that. Yeah. Okay. Any more questions? I'm going to move on to the next part, last part. All right. Cool. Pie charts. So pie charts are this thing that I think most of you probably have heard about not using. They're kind of avoid them because there's something bad about them. They might be infectious or something. But the thing about pie charts is that they're used all the time. There are literally millions of pie charts being made this very moment. So it's silly to, I'm serious. It's silly to just Google pie chart. You're going to find like even just 3D pie charts. There are millions out there. But so it's silly for visualization researchers to say, well, no, we're not going to touch them. They're But why is that, right? I mean, why are pie charts this bad thing? Well, it's because a lot of people just misuse them. And so here's an example. This is one of my favorite pie charts. I got this from Wikipedia. This is all the US states by population. And it's such a great example because it's obviously too many slices. And you can look at the colors and you're like, oh yeah, this is not working. And you can look at the first few, and the problem with pie charts very often, just like with maps, but I'm going to spare you that rant right now, is that they show you what you already know. So we know that California and Texas have are the two biggest states by population, and then you could guess the next one or two perhaps, and then it gets more interesting because you're like, okay, wait, Illinois, I didn't know that, and Pennsylvania. So that's where the interesting information comes in as kind of ranking. But that's pretty much where it ends, because then you get to the point where all the slices are pretty much the same, and you can't even tell them apart anymore, so you can't really tell how many more people there are. And it just becomes a ranking. You might just make it a list. It's just maybe a cooler shape, I guess, than a list. And what's also cool about what's interesting about this chart is that whoever made this chart put this label up there that says other. And so they realized they couldn't put all those labels up there, but they still made all the slices. And this is really interesting to me because there is this weird disconnect in terms of how we think about visual representation, that we just think we just make that chart and it's going to do something. But with the labels, we know that we can't fit them, so we'll have to figure something out there. So that's one thing. And then elections, of course, are always fun because you get all these charts. This is famous pie chart that sums up to 133%. And it's funny because, of course, the problem here is that the representation didn't actually fit the data. Because what they did is they asked people who they wanted to run, but they could name one or two people. So these categories are overlapping. This is not a correct representation of the data, which leads to these kinds of problems. And people say, well, it's the pie chart's fault. But it's not the pie chart's fault. It's not that. It's the people who make those pie charts who don't understand what they're for. And just to show you a positive example here, this is from Canada, where they do this stuff better. This is the before and after picture in Alberta in 2015, where you can see on the left, and this is actually interesting for a number of reasons. First of all, it's donut charts, and they're even worse than pie charts. And then there are two of them, and you're comparing them. But because the numbers are so different, so on the left is before the election, and on the right is after the election. But because the numbers are so different, they're easy to compare. This is not a matter of some fine detail. This works because it works for this data. And that's part of my argument here, is that sometimes these charts can work just because the data is so different. Each of those individually also works because the values are so different. So if the distribution is like huge value and then a bunch of small values, that's great for a pie chart, and especially, or a donut chart, and especially if you only have like 5 or 6 like here, then there's really no reason why they wouldn't work. And what's interesting, what I just said about the donut chart, is that people will tell you that donut charts are a bad thing because obviously we read pie charts by angle, and when you take out that center of the pie to make a donut, which is apparently how you make donuts, you lose that central part where you can read the angle, right? So that makes sense, but then that leads to a question, like, how do we know this? Is it actually true? And so we did some research. So we looked at a pie chart and said, well, so a pie chart has the angle in the center. That's something we know, and that's how we draw them. We figure out what the angle should be as the fraction of the total thing, and then we draw that thing. But it also encodes the arc length, and it also encodes the area. So there are 3 visual cues here. There's a fourth one, but that's pretty much not very interesting. It's called the chord length, which is the straight line connector between those 2 endpoints of the arc. But the question is, so how do we know that it's angle? What's the reason? Why do we just hear that? And you will hear that. You will see that everywhere. If you any book you open and it talks about pie charts, it's going to tell you that. And it's either going to not give you a reason, it's not going to give you a reference, or it will reference one particular paper. So to tell you about the history of the angle in pie charts, I want to introduce you to Mr. Walter Crosby Eales. He wrote a paper on the relative merits of circles and bars for representing component parts for the Journal of the American Statistical Association. And he wrote it a while ago. This was in June 1926, 90 years ago. Okay, that's pretty amazing. There aren't a lot of things that we still rely on that are 90 years old. And so we decided, we in this case being my students, as I told you, I'm still sort of a professor, I had my last remaining PhD student who just defended his thesis 2 weeks ago, and he's finishing up in the next 2 weeks or so, hopefully. We had these 2 papers at Euroviz earlier this year where we looked into that, and we asked, well, which one is it, and can we figure this out? And I want to walk you through this a little bit and show you a bit of the thinking behind these things. So pie charts, right? We have these different cues that we encode. So how do we test them if they're all the same? So what I forgot to say earlier is that as you change the angle, the arc and the area change at the same time, and they change at the same pace. So they're all linearly dependent on the angle and on the value. So there is no way to tell them apart usually, unless you're smart and you can break them apart. So we made a number of these stimuli, these images that we would show people and ask them what's the value. So we have a baseline pie chart here, and we have a baseline donut chart. These are just there so that we have something to compare to, and also so we can compare the donut to the pie. And then we said, okay, we need to break those up. And there's a long process here. This took 6 months or so. But the final result was that we had 2 charts that were arc length only and area only. So the bottom left here is arc length only, because it basically only has that arc. And then the bottom right one right now is just the area. And the idea is that we fill up that circle to that fraction that we want. And then all of those things, by the way, we spin them around. So they're all at random angles. We never keep, so this is just an example here. They're not always at that angle. And then the last one is to say, well, but then we also need to ask about, so we have arc length only and area only. We also need to ask about angle. So here's angle only. And angle only was the most difficult one to design. But what we have here in the bottom right is the angle section, essentially just 2 lines of the pie chart. And these little teeth you see there are supposed to be arrows that point towards the side that we ask about. Because if we don't put that there, you don't know which part are we actually asking about. And the same thing is true for the top right one, which is the same idea for the donut version, basically, of it. So we took out the center of the chart in the bottom and put it up on the, and that's the top chart. If that makes sense. So I want to walk you through some of these results because this is still fairly recent work, and I want to just show you what the actual results were. So we ran this study. There's this thing called Amazon Mechanical Turk, if anybody's familiar with that, where you can have people perform well, not just studies, but all kinds of tasks that computers can't do. Like there's a picture of a hammer, and the description of a hammer is just the same thing that they're describing and stuff like that. And what we do with that is we run studies on there because we can get people to do these things very quickly for fairly reasonable pay. And after looking at the data, what we found is this. So this is, I'm going to try and explain this without going into too much detail. But what you see here are confidence intervals. So the range of these values is important, and they can be compared to each other. And the important thing is that when they're overlapping, we cannot tell them apart. But when they're not overlapping, then it's important because then we know they're different. And you will see that there are a few that are very different, and that I think will be clear from there. So what we are seeing here is this is what's called absolute mean error. So what we do here is we ask people what percentage are you seeing here, and then we show them lots of different examples, and they type in some numbers, and we now take the difference between what is actually shown as a percentage and what they told us. And we take the absolute distance between those things. So we always count it in the same direction and do the mean of those per person and then across everybody. And this gives us an error measure here. So this tells us how far away people were. So about 4 percentage points is the deviation here, or is the lack of precision here. And so we got this for the pie chart, and we got this for the donut chart. And this is interesting because they overlap. They're pretty much the same. The difference here is not in any way significant. And then we got this for the arc chart and this for the area. And that was interesting, especially the area, because the area, if you read all those books about perception, they will tell you that area is very difficult and that we're actually really bad at comparing areas when the shapes are different. And of course, the shapes are different here. So that's arc, that's area, we're missing angle. And that's what that looks like. Just to draw this little band here, this is where the baseline chart is. So you can see that we're several orders, not orders of magnitude, but several standard deviations away from that value. So we're clearly not using angle to read these charts. This is new research. We just figured it out 90 years after somebody did a little study. But a lot of books have to be rewritten now because this is no longer true. We now know that it's not angle. And I've done some follow-up work that is currently under review, so I shouldn't talk about it too much. But well, you will see this also in the next one, I guess. But I can say it was almost, well, as much certainty as I can say as a researcher who doesn't overstate his claims too much, is that it's area. So we read these things by area, and I have some other studies that I'm preparing to figure out if we can actually nail it down a bit more. But we have a very strong indication that it's area. So even though we can't tell it apart here, of course, we don't know from this study which one it is because they both look the same. So this is really interesting because we show very clearly here that angle is much worse than angle only is much worse. And this is even with some help. So we found that a number of people were judging the wrong side, and so we actually corrected for that. So we basically gave them all the benefit of the doubt to make this as good as possible. And still, this is the way this looks. And then so to summarize this, what we found is that if we put all these things together, we found that essentially all of these things here are the same, or at least they're not we cannot tell them apart. We can't tell that they're different, but they're all better than the angle. So this is just kind of the visual summary here of that. And then and what's also important here, or interesting here, is that it's consistent within itself because the donut chart is no worse than the pie chart, which makes sense because if it's not angle, then it doesn't matter if you take out that center. It's not that important. But we wanted to ask that question a bit more specifically, and we said, well, what else could we try? And so we just did another study, and I'm not going to walk you through these results as much, but we just basically took a bar chart and we started to We took a pie chart and we started drilling bigger holes into the center, and basically made different versions of donut charts, and we found that they're pretty much all the same. This is an oversimplification. The last one actually isn't. It's a bit of an outlier, but it's very close. And if we had run a few more people, it may have been different. So I'm not very confident about that last one. But everything else is the same. There's really no difference. So and that, again, is a very strong indicator that it's, again, not angle. This is totally consistent with the first study. And so we said, well, OK, now we know something. So we can make predictions. And that's not a thing we usually do in computer science. But we can do some science. So we can try and actually say, well, what if we could actually predict things that could happen? So we did another study and said, well, let's see, and this is going back now to presentation, what do people do in infographics? Well, they use pie charts a lot, I can tell you that. And they do things like this. They have a pie chart, and they want to emphasize one number, one slice. And the emphasis is by making that slice bigger, right? If you read the pie chart by angle, that doesn't matter. But if you read it by area, that's a problem. So, or by arc length. So we drew our version of this because we didn't want to have color in there and stuff to make this more complicated. And we said, well, we probably are going to get an overestimate, right? This is our prediction. Let's test that. People also do these things, exploded pie charts. And different people will tell you different things about this. We don't really know if they're a bad thing or not, but we figured, well, let's just try it and make a version of that. And we didn't expect a difference there. So we just said, well, there's probably no difference, but we'll see. We'll just try it. And then people like to do these things, where you have a shape, and the shape is your pie. And you have a number represented on there. By the way, the interesting thing, I hope this is visible. Yeah, the white proportion of this is the 80%, not the blue portion, which is kind of interesting. But because I would always expect the higher contrast part to be the value represent. Anyway, so we created these two versions here. This is not a 3D pie chart at the left one of these two, but it's an oval, basically. So we drew a pie chart, and then we just cut out this ellipse, and we cut out a square. And the idea was to say, can we make something that is irregular in terms of how the different things, the different cues that are not angled change? And that's what this was for. And then we had a baseline pie chart as well, just to compare to. So in all, oh, there we go. That's the baseline pie chart. Sorry, I was looking at the wrong image here on my. display there. So we expected more error for the irregular shapes, and then there's our baseline pie chart. So very briefly, what did we find? Looking at this is a bit of a different version of this. We're looking at bias here. So bias is now the error, but not absolute error. So we took the errors and we added them up so that negative means one direction, positive means the other direction, and we did the average. And so that tells us which way do people over or underestimate values. And then in this case, I collapsed the baseline, the pie chart, so that we get a line. That's actually the correct way of comparing confidence intervals. And when you look at this, there is a very clear outlier. Well, there are kind of two, but there's one that's a very strong outlier, and that's our friend, the chart with the bigger radius. And this is, again, consistent with the idea of angle not being it, because angle was not tampered with here. What we tampered with was the area and the arc length. So we very, very strongly, very clearly overestimate those charts. And that's a very good hint here that that's a problem. What's also interesting is that there's a bit of an underestimation here, a bit of a bias with that square chart, but it's not entirely clear where that's coming from, but it's an effect that we found. And if we look at absolute error again, so this is the error that where we just go either way, it always adds up in the same direction, we see that the error that's introduced by all three of those variations on the right there, so the exploded pie chart and the two irregular ones, is quite a bit higher than the baseline. So that tells us that that's a bad thing to do. So and it's not that unexpected, but again, it's consistent with the angle not being the point. I'm going to drive this home a few more times. But it's because if it was angle, there would be no reason why people would have more error if the shape is irregular, because we haven't changed that. We did not interfere with the angle. So this is published research. And the data is available if you want to look at all those results. We have that all online. You can see that, and I can send you the links to that. But I think what we've done here is to figure out how does a particular technique actually work, and then what does this tell us for actually creating something with that. And that was really the goal behind this. So there's a little summary here. So we found that we get overestimation if we have this larger slice. We get larger error for exploded pie charts and for the irregular shapes. And the interesting thing really is that the donut chart is just as good or as bad as the pie chart. So if anybody who says pie charts are okay, but donuts are, you're crossing a line there, tell them about this because it doesn't matter. And there's other research. So we're not comparing with other chart types here. So this does not say anything about error in general in pie charts. But as long as you stay below a certain number, and I don't have a very strong cutoff here, but if you stay within a certain number of slices and you don't, and the values are different, they also work pretty well, and if they're big enough, because you have to be able to actually see them. And finally, we found that it's not angle, and that's a really interesting result, I think. So to wrap up here, I'm going to return to a slide from earlier, not this one. But what I was trying to tell you is that presentation is a very different thing from analysis. It really is not just a matter of I'm just making things bigger and using more colors, but it's really a matter of what do I want to achieve. And that means, do I need to engage people? Will people look at this without making it more interesting? And will people remember it? Because if you show stuff to people, you want them to actually take something away. And that can be helped by using certain techniques. And these were just examples. I'm not saying that those are the only ones, certainly, or the best ones, but they are ideas, and there's a lot more out there. And if you look a bit at news graphics, they're doing a lot of interesting stuff there, where you can play with different ideas and just do things that are a bit more unusual and a bit outside of that mainstream. Speaking of which, I do a different talk as well on tomorrow and on Thursday. It's called Data Journalism. It's in the program. It's called Creating Awesome News Graphics in Tableau, but it should really be called Recreating, because that's what I'm doing. I'm looking at a few examples, and then I'm showing you how to do those in Tableau. And then I'm going to repeat this session here as well tomorrow, if you want to send your buddies. And then last point here is, please complete the session survey. This is very helpful for us. And I'm happy to take questions for the next few minutes. And then you can also find me online and email me and stuff, of course, as well. But I'm happy to take questions right now. And we have a microphone, and thank you.
Just a couple quick questions. Did you look at reaction time at all? response time
For pie charts or for which one?
for any of the data that you?
Yes, we did. We did, well, we did not find, so yes, we did. I cannot tell you a very clear, I can't give you a good response right now about what we actually found because I can't remember right now. We did for the isotype in particular, we looked at the comparison between isotype and bar charts, and we wanted to see if people were faster with bar charts, and I think we found no difference there because that was one thing we expected to find. With pie charts, I think we looked at it after the fact, but there was nothing interesting in there from what I remember. And then for connected scatter plot, because some of those were qualitative studies, we didn't do much of that. So there may be something in the paper, but I don't remember right now.
So with your pie chart where you did the comparison, comparing between the two, that violates proximity compatibility principle, right? So I would usually recommend not doing that. I mean, you can do it, but the accuracy is going to be down. If you measured that versus, say, a grouped bar chart, because you separated out the marks that you need to compare, right? Right. So they're big enough. You can certainly say bigger, smaller.
Right.
But in terms of sort of accurate
Okay,
proportion
right.
difference.
Yeah. But so my argument here is that because the values are so different, it kind of doesn't matter. So there's a point where, because if you look at like the PC there, they went from 70 to 10, right? So you can see that you could probably ballpark that pretty close to that factor. Yeah, but I'm not arguing that we should be comparing pie charts or donuts, but in this case, I think it's less important because the values are so different between the two. But yeah, I certainly don't disagree with that. Yeah, there's one over there.
Yeah, I was just curious if you saw any of the your results. Did you try them with more than 2 slices to see if the results like bore themselves out or got worse with an increasing number of slices?
Right, we did not. So this is because we were really focused on this one question, and it's hard to even get those things into one study. So we decided to just go with one and just just not go beyond that. I doubt that there's a difference because we were really looking at kind of a fundamental mechanism, and we would probably find very similar things. That's my guess. I can't say for sure, but I don't expect any differences there. It might be if you have lots of slices and they get very small, then of course you're going to get a lot more error. But yeah.
Just a quick question about the connected scatter plot. So do you feel like when it works, it's because there's some mathematical relationship, like maybe it works when in general one variable moves with another, and then really what you're trying to highlight is something happened to change that relationship?
Mm-hmm. Yep. So I think when it works, there are a number of things here that I don't have the images here, but if you look at the two, essentially you're plotting 2 time series against each other, and when there's a reason why one is lagging behind the other, you get these loops, or at least you get them sometimes. You don't always get them, and they work when there is a certain amount of complexity that makes it interesting, but not a big hairball. So if you have lots of crossing lines, it's a problem. If you have none, it's also boring. But if there, and I've been looking at like what kinds of metrics are there that could tell us that, and I have a few, but it's hard to find like what are the parameters, like where should they be, what kind of range should they be in. But yeah, there's certainly patterns in there that are interesting, and we've been looking at that a little bit, but not enough to really have a clear answer yet. But yeah, we would like to be able to say, well, look, this data set looks like it might work, so try it out. That would be awesome, but not quite yet. I think there's one more back here.
Did you look at differences in perception between different types of audiences, say a professional audience versus a lay audience?
So differences between audiences, no. This was all, you mean for which one? For any of the particular ones or just in general? Sure. Yeah. So we did not, we did this a little bit for the connected scatter plot because there we ran a few things in the lab at Northwestern and then a few things online on Mechanical Turk. And we did not find a difference there. Because we're doing fairly low-level stuff, we expect those things to work across people for the most part. But for anybody, but of course there's always some sort of bias. If you do it at university, you have much younger, much more educated people. If you do it on Mechanical Turk, your age variance is much higher, which is good, but also your average age is much higher. So you're going to get a very different population. But we expect those things to hold across everybody. I don't think that there's a reason especially because they're very clear results for the pie chart and for all of them, actually, isotype as well. There's 2 more here. Let's just get the microphones, because we're recording the talk, so we want to get the
So can
questions
you
too.
flip, I think it's to the next slide, where there's a published,
Are you looking for the helium chart?
that one.
Yeah.
Did they do something that kind of tortured the axes? That one I'm trying to figure out. I mean, is there,
You mean that gap, or?
yeah, to get that plot, I couldn't figure out if they had to do strange things with, I guess not,
Is
the
it-
axes.
I'm having trouble seeing my mouse pointer, but you're looking for the gap in that line, or what are you looking
I just didn't
at?
know if they had to do some creative things with the axes to get it to do that, or is
I don't
that's actually how it
know.
plotted out? Okay.
I haven't noticed anything, but I'm
So, sorry. Yeah, I just wanted to look at it again.
okay. Sure. I think there was a question back there too.
Thank you for the presentation. I was just wanting to see if Edward Tufte has influenced any of your work or that of Tableau.
This is all stuff that he would be like jumping and screaming here. So okay, I'm being recorded, so I'm gonna keep this civil. But the problem is that Tufte has these ideas that are based mostly on his own instincts, and he has good design instincts, but he doesn't know the research, and he certainly doesn't know any research that's less than 20 years old. So there's a lot of stuff that we've done in the meantime that needs to update people's perceptions. And of course, Tufte would tell you, I think one of his quips is, the only thing that's worse than a pie chart is 2 pie charts. Well, yeah, sometimes, but it's not always the case. And again, this is all based on ideas from really pretty much the 70s. So we need to update our thinking, and we need to move beyond a bunch of books that Tufte wrote in the 80s for the most part, and look at what the evidence tells us. And the evidence tells us that he's wrong about many things. And there are other use cases. The other thing is that Tufte is very focused on a very particular use case. And there are others that are also valid and that need to be acknowledged, and we need to understand how they work. So there's a very big disconnect there. And Tufte has done a lot of good things for visualization, but he's also holding the field back now. I think for the last 15 years or so, he's just been really holding back what we're doing. And that's why I like the monster so much, because he hates it. And it's become this kind of this crystallization point of new work that's looking at memorability and other things and says, well, there's a world beyond Tufte. There's a big world beyond Tufte. Okay.
We could take one more question.
One quick one. Nobody wants to argue with me about Tufte? All right. Well, thank you all. I appreciate it.